Today we will study with electrostatics of conductors. We know conductors are made up of mobile charge carriers. In metallic conductors, these charge carriers are electrons. When electric field is applied, the electrons drift in a direction opposite to the field. Let us see some properties. First, inside a conductor, electrostatic field is 0. Let us take a conductor ABCD. An electric field is applied across the conductor represented by E0. In presence of field, the free electrons will drift in the conductor and accumulate on the face AC. An equal amount of positive charge will develop across BD. Due to this drift, an electric field is set up inside the conductor in a direction opposite to the applied field. The electrons will move until and unless EI does not becomes equals to EO. When field inside becomes equals to the applied field, the electrons will stop moving. And as a result, the net field will become 0. Okay. So if we apply the field, what happens? The electrons will move in presence of electric field and the charge is so distributed that the net field becomes 0 because EI is equals to EO. Electric field inside is equals to electric field outside. Hence the net electric field is 0. So always inside a conductor, electrostatic field is 0. Next property. The electric field is always normal to the surface of conductor. If you take any charged conductor, field must be normal to the surface at every point. Okay, let us start with a contradiction. Suppose the field is not normal to the surface. Okay, in this case, you can resolve field into its components and we will see there will exist a non-zero component along the surface. Let us take a surface. Okay, we choose a small element and field is not normal to the element but it is at an angle. So we resolve this field into its components. Suppose it makes an angle theta with one of the vectors with the normal. Here the component which is along the tangent, this will make the charged particles move. Okay, the free charge on the surface of the conductor will experience a force and hence they will move. So the charge will no longer be stationary now. Charge will not be at rest, it will not be localized, but it will start moving on the surface, which is not possible. Let us write mathematically. E parallel component is E cos theta and the other component which is tangential to the surface is E sin theta. Okay, now we want that this sine component should be 0. Only then the charges can remain at rest. So if you take the sine component to be 0, now electric field is not 0, it means sine theta should be 0. And if sine theta is 0, it implies theta should be 0 because we know value of sine 0 is 0. Okay, so if theta is 0, from the figure you can see the vector E will be normal to the surface. Okay, so electrostatic field will always be normal to the surface at every point. Next property, the interior of a conductor has no charge in the static situation. Means in a conductor no charge can be present. Now we know that field inside the conductor is 0. If you imagine a closed surface inside a conductor, the flux through the surface will be 0. If field is 0 means flux will be 0 because flux is E into ds. Okay. Now Gauss law says that flux is Q upon epsilon naught. So if flux is 0, it means net charge will also be 0. Okay. So in the conductor, no excess charge can be present in static situation. Okay. Next property, electrostatic potential is constant throughout the volume of the conductor and has the same value inside as that on the surface. Okay. Now inside the conductor we know electric field is 0. This is very important property. Okay, inside the conductor field is 0. We have just seen in the previous case that the tangential component of electric field, that is a component along the tangent to the surface, is also 0. So field inside is 0 and the tangential component is also 0. What does this mean? It means that no work is done in moving a test charge within the conductor or on its surface, because we know work done को हमने कैसे लिखा था, E into dr. तो अगर इलेक्ट्रिक फील्ड 0 होगी तो वर्क डन भी 0 होगा. ठीक है. अब पोटेंशियल डिफरेंस को कैसे डिफाइन करते हैं? वर्क डन पर यूनिट चार्ज. ठीक है. तो अगर वर्क डन 0 है मतलब पोटेंशियल डिफरेंस भी 0 होगा. तो पोटेंशियल डिफरेंस इज 0 बिटवीन एनी टू पॉइंट्स इनसाइड और ऑन द सर्फेस ऑफ कंडक्टर, और यू कैन से पोटेंशियल इज कांस्टेंट. ओके, if potential difference is 0 means potential is constant. So this proves the fourth property, that potential is constant in the volume of the conductor and has the same value as that on the surface. Okay. Fifth property, electric field at the surface of a charged conductor is sigma upon epsilon naught into a unit vector n, where sigma is surface charge density and n is the unit vector normal to the surface pointing outwards. Okay, the same result we had obtained due to a hollow charged conductor. On its surface also electric field is sigma upon epsilon naught. गॉस लॉ के एप्लीकेशन में हमने ये रिजल्ट पहले डिराइव किया हुआ है. अब हमें ये रिजल्ट किसी भी surface के लिए, whatsoever be the shape of the surface, electric field on the surface will be sigma upon epsilon naught. So let us take a surface. It carries a charge. Now to apply Gauss law, we will choose a Gaussian surface which we take it as a cylinder. Okay. Now it encloses some charge. Let the surface charge density be sigma and electric field points normally outwards. Let the area of its top and bottom surface be delta S. Okay, so what we have taken? We have taken Gaussian surface is a cylinder. You can see one end of the cylinder is just outside the surface and the other end is partly inside the surface. Okay, so Gaussian surface जो है, जो सिलेंडर है, उसका एक एंड सरफेस से बाहर है और दूसरा एंड उसका सरफेस के अंदर है. ठीक है. जब हम इलेक्ट्रिक फील्ड निकालेंगे तो हमें सिर्फ आउटसाइड सरफेस से निकालनी होगी. वी नो दैट इनसाइड द गिवन सरफेस इलेक्ट्रिक फील्ड इज 0. ओके, सो जस्ट फ्रॉम द टॉप फेस वेयर वी हैव मार्क्ड द वेक्टर E, वी वांट टू फाइंड आउट व्हाट विल बी द इलेक्ट्रिक फील्ड. Okay, now according to Gauss law, we know phi is E into ds. We also know that phi is Q upon epsilon naught. Okay, so in place of Q, you can write sigma ds. Sigma is surface charge density, so it is charge per unit area. Okay, so Q can be written as sigma into ds. When you simplify, ds cancels off and result is E is equals to sigma upon epsilon naught. Okay, when you write it in vector form, electric field will be sigma upon epsilon naught into the unit vector n. Okay, this n is pointing in the direction of the vector E. Okay, last property, electrostatic shielding. Shielding means to protect certain region from the effect of electric field. Let us take an arrangement. You have a hollow region enclosed by a metallic surface. Okay, this hollow region is called cavity, and whatever be the shape or size of the cavity, the electric field inside the cavity is always 0. There may be charge present outside. You can see in the figure also that charge is present outside. There is some negative charge density on the left side, positive charge density on the right side. Means outside this cavity charge is existing, there is existing electric field, but inside the cavity the field is 0. Okay, you can take another arrangement. Suppose you place a charge inside cavity by certain means, then also the charge cannot exist inside this hollow region. It will induce a negative charge on the inner surface of cavity and a positive charge on the outer surface. So the net charge inside will become 0 and entire charge is transferred to outer surface. That means inside the cavity always charge will be 0. If charge is 0, electric field will also be 0. And this region can be protected from the effect of electric field. That is why it is believed that during lightning, it is safe to be inside a car than under a tree. Okay, if you are inside a car, the body of the car forms the metallic conductor and inside is the cavity where charge and electric field cannot exist. So you are safe, you are protected from the effect of heavy charge or electric field produced by lightning. Okay, so protecting certain region from the effect of electric influence is referred to as electrostatic shielding. Okay, whatever be the charge and field outside, cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always 0 and this is known as electrostatic shielding. Okay.